All right. So yeah, first of all, thanks for inviting me to talk a little bit of our flight journey at Roboception. So yeah, happy to talk about why we chose flight, and hopefully this is of interest to some of you. And of course, if you have questions during my talk, feel free to post it in the chat. Unfortunately, I cannot see the chat while I'm sharing. But yeah, if you have some questions, just feel free to interrupt me in that case. Or otherwise, we can also discuss questions at the end. Also, if we have questions later, you can always hit me up on Slack or something like that. All right, so let's get right into it. So I'm going to briefly talk about our company, so what we do, our portfolio, so you get a rough idea of what we use Flyte for. That would be our cut match program, so I'll briefly introduce that. And then I'm briefly going to talk about what we've been using so far and why we needed something a bit more powerful, I would say, a bit more flexible. I'm briefly going to talk about our local Kubernetes cluster setup, and I hope that this is useful for someone. And yeah, how our Flyte workflows for our heterogeneous local GPU cluster currently looks like. And then sort of like some to-dos that we have to do on our side to fully leverage what's already there in Flyte, and then some things that we would like to see in Flyte in the future. All right, let's start right off. Yeah, so I'm with Roboception. We're a rather small company, founded in 2015 as a spin-off from the German Aerospace Center. And yeah, we make 3D sensors and mostly software-based on that. So an idea is that basically we go from pixel to action using perception. And we're based in Munich in Germany. So just briefly, that you have an idea of what we do. So we have a hardware line of 3D stereo sensors. This is the RC Wizard sensor family that you see in the middle there. That's basically a smart camera, so that has a processor on board with a NVIDIA Tegra GPU on it, so we can do some processing on the camera directly, and you don't need an extra external industrial PC. And also we have a software suite of things that run directly on the camera that ranges from like very simple things like detection of tags, APRIL tags, QR codes, and so on, to sort of like very simple picking scenarios using item pick that just detects basically surfaces that are graspable with a suction gripper, to the more complex at the very end of the spectrum, which is CAD match. And that actually is basically what we use Flyte for, to train our models for CAD match. And that actually then needs more resources than we have available on this smart camera, at least in this iteration, and will run on this extra industrial edge computer that we have. And yeah, we also have a standalone stereo sensor that has a bit more resolution. Okay, so briefly, why stereo? I guess this is quite interesting in terms of image processing. Might be obvious to most of you, but traditionally in robotics, and especially in industrial automation, a lot of stuff is done either with 2D cameras or with laser scanners. But of course, if you have a stereo system or any system where you have a camera image and depth information at the same time, that makes it rather nice to sort of like combine classical algorithms that can certainly shine in terms of speed and robustness in some scenarios with machine learning in one system. So on the bottom here, you can see this is a normal camera image of our monochrome camera, and sort of like the color depth images for us to look at as humans. And then also for every pixel in the depth image, we have a corresponding confidence image and also an error image not shown here. So for every pixel, we know how confident we are that the error that we report is actually true within the 3 sigma bounds. And yeah, on the right side, you can see like a 3D reconstruction of how the spin would look like. Okay, so now where does Flyte come in? So for our CAD match program, basically the idea is that usually you have parts that you know before. So for example, in manufacturing, in machine tending, where you need to recognize known parts, usually lying random in the bin. For example, insert them into a machine or somehow process them, put them together or something like this. So the idea here is that the customer provides us with a CAD model, and then we train several machine learning models, learning networks, and we have a classical algorithm on top of that. And in the end, basically, we have a very easy to use web-based UI that the customer can use to sort of like set up the system, define points, how the object should be grasped and sorted and so on. But that's sort of like the background. Let's see here how this looks. Unfortunately, this is, I guess, the it's a bit of a shame. That used to be a GIF, an animated GIF. I guess it didn't go through in the PDF. But we have basically two main stages. So first, we detect objects where they are roughly. So this is a simulated image. So that's usually a bounding box, or it could also be a segmentation mask. And then in the second step, we have a refinement that is usually done with classical algorithms to get something more precise out. So this is a bit more detail. So in stage one, basically we do this bounding box detection, and then we have a neural network model that sort of like estimates the rough size, rough orientation of the object. And then in stage two, we use edges, the depth image that we have, and all the extra information with classical algorithms to refine it to get a more accurate and more robust result, and also do some sanity checking and so on. So basically, we use Flyte for stage one to train our modules and also for the evaluation. So this is basically the things that we need to go through. So we get a CAD model from our customer, then we do like some synthetic data generation in the simulation environment. Then we train our neural networks, and then we run evaluation. And in the end, basically we get what we call a template that basically contains our neural networks, parameters for the classical algorithms for the refinement, also stuff like the CAD model to show in the web-based visualization and so on, and also a simulation report. So basically you can pick use cases that you want to have evaluated in, like how far away will it be with the camera, how large will the objects be, is it a random bin, or do you have some prior knowledge that might make this a bit more accurate or so. So we can get a pretty good idea beforehand, even before the customer got the first camera or used it somehow in their real setup, to give a pretty good estimate of what the expected working range would be, how accurate it would be, how fast it would be, and so on. And this is basically, this generation is what we want to represent in Flyte. So a bit further, so here our simulation environment, this is mostly done in Blender, but also some direct, bit faster OpenGL rendering and so on. And we have a very large material library of different basically background scenes that are common in industrial automation. We use that to simulate a large amount of data. So we use that for training and also for the processing and evaluation. That also means here on the left side, you see the two left and right images. So since we have a stereo camera, we have a left and right image. Then we also simulate some sensor noise based on how we know how well our cameras work, what the expected noise level would be. And then we run our actual stereo algorithm on these simulated images. That's basically the image that you see, the third image from the left. And then you also get sort of like naturally all the occlusions that you would have, or the shadows where you don't have any real data points. just if you would see them from the real camera, just because either there's overlap or some other things. And then on the right side, you can see sort of like our evaluation. So we detected the parts in there, and then since we have the real ground truth data from where the object actually is from our simulation environment, we can easily create a report and judge how good this template. So the whole of the two network models, including our classical refinement, in the end works in a specific setup of the customer site. All right, now for the interesting part for most of you, hopefully. So how did this look before we chose to go down the Kubernetes and Flyte route? We already had our individual tasks, so that, for example, training of one specific network model, containerized. All the data lives in our MinIO cluster, so that's an S3 compatible object store that we run on premises. And we had some very simple scripting around Docker Compose and some queuing scripts and so on, to sort of like run these steps one after another on different GPU machines that were currently available. And we basically then coordinated amongst us with a small team. So this is still possible of who's using which machine to train something or generate some templates and so on. Yeah, so the pain points, as you can imagine, of course, we have several GPU-enabled servers here, and this sort of like manual distribution, choosing where to run what, definitely results in suboptimal utilization of these GPU machines. It overall takes longer if you want to get something done quickly for a customer. And some of these jobs need much more GPU memory than others. So there is always a bottleneck, and you have to take care if somebody's already using that machine, that you have to wait for that. And in general, sort of like this manual scripting stuff and so on, we lack a good overview, and we wanted to use some proper workflow orchestration tools and some workflow tooling on top, then to build an internal self-service platform where also our non-technical, for example, sales could just sort of like drop in one CAD model, and in the end there pops out a report including the trained models that are in this template. Okay, so before we chose to go with Flyte and check that out, the question in the beginning was, what kind of orchestration solution do we even want to use? Basically, do we want to Kubernetes or not to Kubernetes? As you all probably know, if you've done this yourself, it's quite a powerful, but also quite a complex system. And if things go wrong and you don't know what's happening, that's usually worse than having a very simple system that has some other limitations. So we basically looked into some agent-based systems, which basically means you have an agent running on some machine somewhere that will call or get sent jobs. We also briefly looked at Nomad, which is an orchestration tool, which is quite a bit simpler than Kubernetes, but not that many projects sort of like are based on Nomad or use that as a lower level orchestration tool. And then, of course, what kind of workflow tools that run on top, either this agent-based or some orchestration tool, will fulfill our requirements, which are pretty basic. So we somehow need to run remote workers on different CPU and GPU machines and schedule those. And since we already had everything containerized, so first we were not looking for something to write our tasks at a very granular level directly in Python, for example, because we already had it containerized such that this kind of like fits our needs, and sort of like iterating on a specific model, for example, right now we handle via our CI/CD system. Of course, there's room for improvement. And obviously, since we want to build a self-service platform around it, we want that to have an API, so we can launch tasks and workflows and so on, and query them for the state, so that you don't need to have sort of like the developer access. And even if it has a decent UI, we wanted to have in the end, a bit more simpler UI to just drop in a model and see what the outcome is at the end. So briefly, we looked at some non-Kubernetes, or at least maybe not Kubernetes native solutions like ClearML, for example. That looked at first glance quite nice. Also strong in sort of like how to track your experiments and so on. It's an agent-based solution, but basically, yeah, it didn't really have good support for containers as a first-class object and so on. It felt a bit clumsy to use it that way. Then also Dexter looked quite nice, but also sort of like the Kubernetes integration in terms of resources to use, what task will run where, seemed a bit lacking, and then updates for that were, yeah, at least at a glance, not so nice. Then, of course, I guess what most people will first find if they Google for something like this is Kubeflow, but that was also on one hand way too much more than we needed, and also didn't seem a bit lacking momentum, and yeah, just in general didn't look that appealing from some technical perspectives. One thing that looked quite promising, at least if we look purely at sort of like this workflow container orchestration thing, would have been Argo workflows. But also then we didn't want our developers to write their workflows in YAML and so on. There's some abstractions around that, but that seemed a bit too low level. Yeah, we looked at Polyaxon, and then actually rather at the end, while already evaluating some others, I came across Flyte, and I was quite surprised that I didn't come across it earlier, but was super happy because that seemed to be a really good fit. So then I immediately tried that out. Okay. So first, before I go into how we use Flyte itself, maybe a brief intermezzo on our local Kubernetes setup. So for me, that was quite a fun learning experience because I've never been working with Kubernetes or anything like that before. And setting that up from scratch locally, yeah, involved a lot of reading and trying things out and seeing what works nicely for us. In the end here, now we have, in my opinion, at least so far works really well, quite nice setup. So we use K3S, which is a very small, basically single binary distribution, originally from Rancher, in a highly available setup. And we run 3 master nodes as VMs in our existing Proxmox cluster that we usually have for other services. And just to make this a bit more, I would say, production grade and sort of like a standard K3S installation, I set up kubevip, which basically can provide you with a highly available control plane, so a virtual IP for that, in case one of the nodes goes down and you don't have the IP for the control plane anymore. So this is taken care of. And then usually K3S comes with an integrated load balancer called Service LB, so it ties right into the lightning talk, which basically is really just a very simple load balancer, so to speak, for services. But for our case, we wanted to have something a bit more flexible. So we have natural LB running, which is quite simple to set up and works really nicely. For ingress, then we actually disabled so K3S already comes with traffic, but I prefer to sort of like manage it on my own. So we just deployed K3S without traffic and then install traffic again for better control via Helm again. And then also, usually K3S comes with a local path provisioner for persistent storage. Since, I mean, like, for example, for the Flyte database, we need persistent storage in the cluster. And that's something that you cannot easily offload to an object store, obviously. So you need something there. The local path provisioner is really just meant for sort of like a very small single machine setup. It doesn't really scale across multiple machines. But thankfully, Longhorn here, also from Rancher, is something that has been working really well, has automated backup integrated and so on. That's easy to set up. So I can highly recommend that. And then, of course, to our actual machines that handle the workload. So we have, I think, right now 6 servers with various GPUs that we had from previous projects and so on as worker nodes. And then there's also some nice plugins. So the NVIDIA device plugin, which does node feature discovery. So that means all your nodes will be labeled with CPU and more importantly for us, GPU capabilities. So then they're just available as standard Kubernetes labels, and you can use those in node selectors or in affinities and so on, which is what we wanted to use to sort of tell which node or work a specific workload should be running on. Also interesting to mention here, if somebody sets this up on their own, there is an extended resource toleration admission controller that you can load into the Kube API server that will automatically add tolerations for attains. So if you request a GPU, usually you add attains to nodes that only GPU workloads or basically something that has this toleration will run there. So this admission controller can do that for you so that your users don't have to take care to specify that in pod templates or somewhere else correctly. And then, of course, you need to somehow respect what your jobs are doing, want to have some metrics and so on. And there, I found that the Grafana agent works really nicely to ship metrics to Prometheus that we already have running here anyway, and also logs to Loki. And then you can basically link that up. So you have a link in the Flyte console, and that will take you to a Grafana dashboard where you can view the logs either live or just for any previous job, and makes it nicely searchable and so on, without all the overhead of putting it into Elasticsearch or something like that. All right, now, so how does our Flyte workflow currently look like? So it's rather simple, not very large. This is basically just our existing containerized setup ported to Flyte. So we use container tasks since we already have it containerized, and some of them don't run Python. So we run, for example, some synthetic data generation, some Blender and so on. So yeah, we just basically have two workflows, one to generate the training scenes. This is the synthetic data generation, and one to train the models. And we put them together in a larger workflow, and on the side to that, we generate some more test scenes that we use for evaluation. And then we have a small task that just goes over some config files that we have in our in MinIO. And then in the end, we run processing on all of these various use cases that we have as test scenes. And yeah, in the end, then we'll get a report out. And of course, the finished template. And this already is so much better to use and easier to use. So we can just go to the Flyte console, start a workflow with some pre-populated default values for some of the things of where to find the config files. And it already nicely schedules it on free GPU machines. So we have to take less care of who's using what, since Kubernetes can really track that if your tasks are properly annotated with the required or the requested and the limits of your resources. Yeah, of course, this is not done yet. So this is just the initial step. We have a few more stuff that currently is not in Flyte. So of course, we'll add this as well. And then we want to use the API, sort of like build a very simple web page where you can just upload the card model, and in the backend it will just trigger that running in Flyte. So you don't need to have sort of like developer-like access and know really what to trigger when. Yeah, we're also looking into leveraging dynamic workflows and some map tasks. I think there's some issues open there to support container tasks, but I guess we'll be able to figure that out soon. Yeah, and then the one thing that is very important or interesting for us, and thanks to Dan for a lot of work on pod template support. So as I mentioned earlier, we have some tasks that need big GPUs, some small ones, or none. None is easy to handle. And since we don't have a very large cluster, it's not in the cloud, and we cannot spin up stuff on demand, we want to really schedule this so we utilize our existing hardware resources well. And just running everything on the biggest GPU possible that we have is not really an option. So the idea here was that we somehow can set a node affinity. So this is basically like a node selector. You tell it on which node to run, but it has more granular ways to select which node, and it doesn't need to be a requirement, but you can also say, I prefer to run a specific node. And the idea is, since we already have Kubernetes labels telling us, for example, how much GPU memory is on a specific node, we use that to sort of like tell small tasks that need less GPU memory to prefer running on small GPUs, and some of them others will then require to run on bigger GPU. And also we need to set the runtime name for GPU tasks. So if you want to run GPU tasks, at least not in the cloud, but on your own, so just like in Docker, for your container runtime, you need to specify which runtime to use. And if you use this NVIDIA container toolkit, this will install a runtime called NVIDIA that will take care of mounting drivers and stuff, correctly exposing the GPU to the pods. Initially, we set that as a default, but it turns out that some workloads that also run on the cluster now don't really like to run the NVIDIA runtime. For example, Longhorn was behaving a bit weird. So we said that better, stay on the safe side and run normal workloads on the normal runc runtime. And we only want to run our actual GPU tasks using that NVIDIA runtime. And that is now also possible then once port template support has also completely landed for container tasks. If somebody wants to go down that route, there would be an interesting alternative. Namely, so I talked about this custom resource toleration or extended resource toleration admission controller before. So that's basically a modifying webhook that will change your pod YAML essentially to inject or modify things. So that injects tolerations. And of course, it would be nice here also to write a custom admission controller that if you request a GPU, that will just automatically set the runtime name to NVIDIA. So you don't have to take care about that in the Flyte level at all. But it looked a bit steep for me right now in the beginning to just write a custom admission controller. And so the idea was that we specify that using pod templates. All right, then, so we have still a couple of things to do to fully leverage what Flyte already provides. And so first of all is, of course, to finish the pod template integration. We have a PR open for the Flyte part, and thanks for Yi and Dan to help out there to test that. Right now, we don't have any authentication set up, so that's also next. We can see who launched which tasks. Right now, it's only a bunch of us. We're not very, very small team, so it's not super important yet. But of course, that is very useful. We're going to see how we can leverage Flyte decks to show some intermediate stuff that we need right now. Just view, for example, via Jupyter notebooks of stuff that is written to our MinIO cluster. And I really, really appreciate that there's already support for signaling, so queuing the loop tasks. Since we have one step that is not in the Flyte workflow, we have sort of like an approval step so that somebody can manually still look over it before it sort of like gets shipped. And then a lot of other nice things like end-of-flow tracking integration and so on that we want to have a look at. And I'm really interested to see, especially how well now this works with sort of like a default Kubernetes scheduler with our limited amount of service that we have. And because often we sort of like put a couple of workflows in the queue, but we only have 5 to 6 machines that can run them. So that will take like 2 days until everything is done. And we'll have to see how well this now works when we can use node affinities, or if we maybe also have to look into a bit more advanced Kubernetes schedulers or how they interact with the Flyte scheduler. There's some nice proposals on the Kubernetes side that might be worth checking out, depending on how well this works out of the box. So we get good utilization and sort of like intelligent scheduling of what runs where without sort of like blocking, for example, a server with a large GPU with a small task and then just delaying everything else. All right, and then maybe for Flyte future specifically, some things that we would really like to see in Flyte, and maybe for some things we can also help and contribute a bit. So far, notifications would be super helpful for us. So we would really like to see support for webhooks. That was also already proposed. If I'm not mistaken, right now notifications are only supported on the cloud platforms, so GKE and AWS. And yeah, also really looking forward to the observability improvements that are starting to pour in, so we can dig a bit deeper on how long is stuff viewed. So also to better get an understanding of where we need to tweak things. Do we need to split some tasks up into smaller tasks to run more of them in parallel? So what's queuing time and so on. So that would be really looking forward to that part. And then also in relation to this, it's super nice to still see, for example, that the task is sort of like scheduled from the Flyte side, but it's actually queued in Kubernetes. Right now, you cannot really see this in the Flyte console. So you need to look into your cluster to see that. And just some small and high things that would really help us a lot to, as developers, as another engineers, get a better idea of why some things are still not done yet and where they are queued. Yeah, just select some small error handling cleanups. I think there's also some PRs already there from Dan or I don't remember who. So yeah, looking forward to that. And yeah, popular request was also that we can terminate individual tasks in the workflow, since we basically grab config external from Flyte from our cluster, and sometimes you just make a mistake there, and you would like to just cancel one individual task, but not cancel the whole workflow, because that would mean like several hours of tasks that are already running being canceled as well. We only want to cancel a specific task. We'll like update our config in the backend, and then sort of like rerun, or rather like recover the whole workflow again later. All right. That would be it from my side. I hope I wasn't going too fast, but I think time-wise it's kind of okay. So I'm happy to take any questions. We have any.
Wow, that was awesome. Thank you, Felix. Is there any question or comment?
I have a quick one, but I think firstly, my name is Ketan, by the way. Felix, great to see you in person here. Firstly, thank you. That the entire journey of how you discovered it and then how you reached conclusion was really helpful for the community. Because this is a question that many people ask us, and every time people share this, great. Second is schedulers. Actually, when we were at Lyft, we had a scheduler that worked with Flyte per se. We never ended up open sourcing that. Yeah, but I think there are better schedulers in open source at the moment, and I think we can create a system that works together much better. So happy to collaborate on that. That sounds amazing. And webhooks, have you looked into the event egress from Flyte and tried to see if you can use that to create a webhook on the custom side?
Not yet. That's on my to-do list to look into it a bit more. First I wanted to get our workflows actually running properly and everything in, and then we'll work on the notification part.
Yeah, and also upcoming in the next release is Python FlyteKit side backend plugins. So essentially you can write the backend plugins in FlyteKit itself. So you could make a webhook as part of your workflow as a step if you really wanted. which could be written in Python and invoke any service endpoint that you want. So let's discuss what would be the fastest way out. I'd love to see how you use this.
Yeah, that would be interesting to see.
Awesome. Thank you. Any other question, comment? Nope. Yeah, thank you so much, Felix. I think I'd like to collaborate with you to produce a blog post or something similar to document your deployment, because I feel that we have instructions for local test environment deployment with Sandbox or production in the cloud, but not something in the middle that will be production in a local Kubernetes environment. So definitely your deployment, it's very interesting. So I will chat with you to see how we can expand the message. But what you have already done in this session is very helpful. Thank you.
Sure. Yeah, my pleasure.